a complicated decision in a sequence of simpler ones. We need instruction on how to make this pairwise comparison. We understand that it's simpler to compare, to take a decision when only two alternatives are considered, but nevertheless we need to be guided in this comparison. And then the pairwise comparison guides us in this way. First of all, there is a scale that is proposed. Which is called the fundamental scale for pairwise comparison. And this means that when you compare two candidates, you compare A with B, you may give a rank, a score of 1, which means equal importance. So, if you compare the experience of candidate A with candidate B, and you find that the two experiences are similar, comparable, have the same importance, you give a score of 1 to A with respect to B. And you see the explanation on the right. The two elements, in this case the two candidates, contribute equally to the objective. You may instead find that candidate A has a moderate importance over candidate B, which means, look at the explanation, moderately, you favor moderately one element over another. You favor moderately A with respect to B. Now, the score of 5 corresponds to strong importance, the score of 7 to very strong importance, and the score of 9 to extreme importance. Okay. You can use also the decimals, if you want, here. And what is more important to specify, you can use also number lower than 1. So 1/3 means that the moderate importance is exerted by the second candidate with respect to the first. So when you assign this score, you compare the first candidate with the second. So if the first has a moderate importance over the second, then you give to the first 3. And to the second, you have to give 1/3. Sorry, I forgot to switch the phone off. I'm providing an example then in a few minutes to see what I mean. But for now, let's assume that in the same way as you say that A has a score of 9 with respect to B, which means that A has an extreme importance with respect to B, you can also, in the same way, you imply that B has a score of 1/9 with respect to A. Okay. Now let me jump to here. And these are the 3 comparisons. So we compare Tom with Dick, and then we say that Tom is 1 as 1, sorry. Yeah, okay. In this case, let me jump, sorry, to the next one. I prefer to jump the previous one because it's a bit misleading. So let me now jump to this. It's more clear. This is the matrix of the comparison. It's a matrix that is n by n, where n is the number of alternatives. And basically, you see the name of the candidates, so the description of the alternatives, in both columns and rows. And in each of the rectangles, each element of the matrix represents the comparison among the candidates whose name correspond to the considered element. So in the case of the top left, you have a comparison of Tom with Tom, and of course the score is 1. And in this case, Tom is alternative A, and Tom is again alternative B. The comparison is 1. If you compare Tom with Dick, then you recognize that Dick is Tom is far less important than Dick, and therefore you give to Tom with respect to Dick a score of 1/4, which means that Tom is less important than Dick, which means basically this refers to experience. It means that Tom has far less experience than Dick. And then if you compare Tom with Harry, you find that Tom has a considerable more experience, and then you say that Tom has a score of 4 over Harry. And in order to do that, what you did is to compare Tom with Dick and Harry. Okay? Now let's move to the second row, which is now brings the name of Dick. And in the intersection between second row and first column, you see the comparison between Dick and Tom. The comparison between Dick and Tom was already done, and we assign a score of 1/4. So for symmetry, in this case, you have to assign a score of 4. If you compare Dick with Dick is 1, and if you compare Dick with Harry, this is a comparison that we didn't do before. So this is a new one, and in this case, Dick prevails. Strong importance, or very strong, I don't remember the description, but in any case, we got at the upper value of the rank that I propose to you. So it means that the experience is much more relevant. Now, let's move to third row, Harry with Tom. We already did this comparison. Harry with Tom was given a score of 4 over Harry. So in this case, we have to give Harry a score of 1/4. And then Harry with Dick. And you see the comparison was already done. For symmetry, you put 1/9, and then again, Harry with himself, comparison is 1. This is the matrix of the comparison. There is one problem here, which could be a lack of consistency. And what could be the lack of consistency in this assessment? The lack of consistency may occur when basically you assign the experience of Dick with Harry. And let me try to better explain. Previously, we compared the experience of Tom with Dick, and we concluded that Tom has less experience than Dick, much less. But then we concluded that Tom has more experience than Harry. So the implication is that Dick should have much and much and much more experience with respect to Harry, because Dick has more than Tom and Tom has more than Harry. So when you come to the comparison of Harry with Dick, if I gave here, instead of 9 in the second row, if I wrote there 1, it wouldn't be consistent. By virtue of the 2 previous evaluations, indeed, I should place a 9 there, or at least an 8. Maybe a 7 is already not really appropriate, but you can't really understand, on the basis of your reasoning, what is the optimal value. If I put there a 7, you wouldn't realize that probably it's not appropriate. you realize that Dick should have much more experience than Ari. But it's not clear to you, even now, if 8 is more appropriate than 9, or 7 is more appropriate than 9. So there could be inconsistency. And if you have a large matrix, with like a 10 by 10 matrix, to ensure consistency is not easy, and it may require an iterative process. We will see how to check consistency. Okay, now let me move to the next problem. On the basis of this matrix, are we able to identify weights, priorities for these 3 candidates with respect to experience? Can we do that? Of course, the reply must be yes. But how can we, on the basis of this ranking, identify 3 weights to give to these 3 candidates? And these weights should sum up to 1. I just would like to remind you. How to do that? Okay. There is a definition which says, let me see. Yeah, I hope it's still readable, but in any case, I'm repeating what's written there. The weights are given by the right eigenvector of this matrix. I am fully aware of the fact that speaking of eigenvectors is not the best topic you would like to speak now. And I don't want to put much emphasis on that. Eigenvectors can be very easily computed with R and with Excel. So I wouldn't go back and provide a definition for eigenvector or eigenvalue of a matrix. Let's just assume that we have to get a software that computes the eigenvector, precisely the right eigenvector for this matrix, and that's it. Okay? And I will explain to you in R because it's extremely simple. You put the matrix in R, there is a R function called eigen, because eigen in R gives to you eigenvalues and eigenvectors. Both are important for us, we will see. For now, let's just keep into account that the right eigenvector, which R will give us, it's providing the weight for the 3 candidates according to experience, and these are the weights. Now, you see that the sum of priorities or sum of weights is 9. Let me just disconnect the Wi-Fi because otherwise we are bored by this continuous. Okay, so these are the eigenvectors. And let me just say that you can get a very similar solution, like a first approximate solution, if you take the sum of the elements in each row and you divide the sum of the elements in each row, which is in the first row is 5.25, and you divide this sum of the element in the first row by the sum of the total sum of the element in the matrix, you get very close to there. It's a first approximation, let's say. So in each row you get the sum, and then you divide by the sum of all the elements of the matrix. But this is not rigorous. The rigorous solution is the eigenvector. Okay, and then there is this inconsistency. What is inconsistency? It's a measure of the inconsistency of the evaluation. And how to measure it? In this case as well, there is another file which I'm opening, the last one, consistency.pdf, which explains how to compute the inconsistency. What is relevant for us is this quantity here, CR. What is reported here, I go back to the Wikipedia file. What is reported here as inconsistency 0.035 was derived, is the same as this quantity CR there. Okay, A is just the matrix, so don't worry about the A between parentheses. And it's the quantity CR, which if it's less than 0.1, 10%, means that the inconsistency is tolerable. And you see that I go back to the Wikipedia file. Here the inconsistency is 3.5%, which means that it's comparable, is tolerable. Now, the question is how to compute the CR. It's extremely simple. Here, the n, the lowercase n is the size, the dimension of the matrix, which is 3. And basically, what you have to do is to get the maximum, the quantity lambda, which is the maximum eigenvalue of the same matrix. Max eigenvalue, and then you compute a quantity which is called, I think, CR, yes, which is equal to lambda max, sorry, here, lambda max minus n divided by n minus 1, it's written there. So you compute this quantity here for your matrix. Okay, and then once that you computed this quantity here, which refers, I go back to the matrix, which refers to this matrix here. You can do another thing, because of course what you have to do is to compare this CR with, which in principle should be 0, this quantity, if the matrix is fully consistent. If the matrix is fully consistent, the maximum eigenvalue is equal to the dimension of the matrix. So this quantity should be 0 for full consistency. We will make some experiments in R, and we will see that if the matrix is fully consistent, indeed the maximum eigenvalue equals the size of the matrix. If the matrix is not consistent, you will get the eigenvalue, the maximum eigenvalue that is higher than the size of the matrix. And of course, in general, you will get this situation. You will have a CR which is greater than 0. And now the question is, how can I judge whether this CR is close to 0 enough to conclude that the consistency is good? So I try to restate the problem. If the matrix was fully consistent, we would get a CR equal to 0 because the maximum eigenvalue would be equal to the size of the matrix. In general, CR is not 0. And therefore we need a criteria, a term of comparison to judge whether CR is close to 0 enough. In order to get a term of comparison, we use a classical approach in computer science in general, which is to compare the result, CR, with the result that corresponds to a completely random evaluation. So the evaluation should be consistent. If I just put number randomly, I get to a situation which is useful to assess consistency, because consistency means that I took these numbers there according to a good judgment. Let me now try to consider a situation where I put numbers randomly, without any judgment, with only one constraint, symmetry. And how to say, diagonality of the matrix. So the matrix should be diagonal with ones in the diagonal and symmetric. This is the only constraint that I put there. But besides that, I just generate randomly. I can do this many times, and then I can compute an average value of CR. Because just one trial is not sufficient. Let's compute 1 million of trials. And each time I compute CR. Again, the only constraint, these are randomly generated matrices, the only constraints are the presence of ones in the diagonal and symmetry. And this, of course, only depends on the dimension of the matrix. So we have a table here which says what is the value of this CR, average CR, that I get with a random simulation. And of course, if the dimension of the matrix is 1 or 2, you get 0, because by just imposing that the matrix has ones in the diagonal and it's symmetric, you complete your matrix. So it's impossible to have inconsistency. But as you get to 3, you get this measure of inconsistency, which refers again to random assessment. This is called RCI here. So this average CR computed with a randomly generated matrix is called RCI. And then the idea is to divide the resulting value. I realize now, sorry, that here I should have written CI for consistency with my notes there. By dividing the resulting value of CI by RCI, I obtain a quantity that is called CR, which is the measure of the consistency. Here, please just note that the denominator of this relationship is called Ri, and I don't understand why they use here a different symbol. It's the same quantity, okay? So the Ri there is equal to RCI here. So just note that. depends on M, of course, while A is the matrix in this PDF. Okay. Any questions?
Is there a big difference between CR, CI, RI?
Okay, yeah, I understand. The symbols, if the symbols are not clear. So CI basically is what I computed here. Basically, you get the, again, maximum eigenvalue minus dimension of the matrix divided by dimension minus 1. This is not compared to any situation, so it's you need to compare it with another quantity to be used as a term of comparison. This quantity is the average measure of CI that you obtain if you generate the matrix randomly. And is called here RCI. Here. And then the only thing that I wanted to make clear is that Ri is the same as RCI. Okay? And by dividing the CI computed here with the quantities that you can get from this matrix depending only on the size of the matrix, so basically divided by, in this case, by 0.58 here, you obtain the measure of consistency, which is called CR. So CI is computed on your matrix, RCI is computed on random matrix, you divide CI by RCI, and you obtain, let me not make a mistake, CR. Okay? So by doing this computation, you get, first of all, let's note that CR less than 10% is fine. You can accept the inconsistency. By doing this computation here, you get this result. And this refers to experience. It's just the first criteria. Now, if one moves forward, now there is the second criteria, education. Again, let me browse very quickly. Here is the matrix. Inconsistency 6%, which is fine. And these are the priority of the three candidates. So let's note here that the best one is Harry, according to education, 73% of preference. Let me go back to the previous one just to see how the situation is developing. Here the best one has been Dick with 71% of preferences. So the question is, who is? Now let's see the other results. So this is again education. And the rest is, as we said, Harley and Dick so far. Let's move forward. And here is charisma, and the best is Tom. Of course, the example is done in a way that each of the three has strength according to some criteria. But this is also a reasonable situation that is credible, because of course if you reduce to three candidates, then it's expected that each of them prevails in some of the criteria, because they are non-dominated solutions. Of course, if you get to three, they are non-dominated solutions. If you have a candidate that is lower than another in all the criteria, you immediately reject the candidate. If you move forward with a so complex decision process, it's because it's difficult to identify the best one. And now let's go to age. I think is the one missing. And this is age. And again, the best is Dick. So one could say probably Dick is going to win, but not sure. We have to make a quantitative assessment. And also there is another issue now. We still have to assign weights to the criteria. Because this is extremely relevant. These criteria have not equal weight. And now we have 4 criteria, of which we have to identify the weights. We can do once again a pairwise comparison. We can use once again a pairwise comparison. But in this case, we have 4 alternatives to assess. And in fact, the remaining part of this file presents to you the criteria versus the goal. So the information matrix is, no, the comparison is here, and here is the resulting matrix. And what is the final result? If you assign to each criteria an importance with respect to the other ones, one by one, you see, for instance, that experience has an importance of 4 with respect to education, has an importance of 3 with respect to charisma, has an importance of 7 with respect to age. And then again, you ensure that the matrix is symmetric, and you make your evaluation. Of course, 4 by 4, it's more difficult. You may have problems to identify consistency. Perfect. Let's move forward, but now we have the priorities here, the weights. So experience is 0.5, 5.4. Education is 0.12, charisma 0.27, age turns out to be not very important. Now, how to summarize the results? This is another important step. Final priorities. It's quite simple indeed. Even if this matrix here may seem like, you know, not really easy to understand, indeed it is not complicated. Basically, you start from the first column summarizes the criteria, and the second column the weight of each criteria. And then what you do is simply get the scores of the 3 candidates. I'm not sure if I have here. Let's see. Yeah, I have a version. Yeah, this is perfect. You see here, you have the scores of the 3 candidates, and they sum. You see Tom with his score, and the score was taken by the matrices that we have seen before. And Dick with his score, you may remember that Dick was the best with respect to experience, with a score of 70% more or less. And Harry with his score, the 3 scores sum up to 1. And then you multiply the scores times the weight of the criteria, and you get here the weighted scores of the 3 candidates. And of course, the sum of the weighted scores is equal to the weight of the criteria. And you do the same for the other criteria, the weight of the criteria, the scores of the candidate. You may remember that Harry was the best for education. And then you multiply by the weight of education, and you get the weighted scores, again for charisma, again for age. And now you may realize that what you have to do is just to sum the weighted scores of each candidate. And to find, or better than to sum, to find the average weighted score. So now what we do, we get Tom, and Tom has weighted score of 0.11 to the first criteria, 0.02 for the second, 0.2 for the third, 0.01 for the fourth. And let's compute the average. The average between 0.119, 0.024, 0.201, 0.015. Let's compute the average, and the same for Dick and Darby. And here is what comes out. So again, you have here the three weighted score, you may recognize that 119, 0.024, etc. And here is the average, or the sum that we see. It's the sum, sorry, not the average, it's the sum. Because the average they are weighted scores, so it's the sum that we have to compute. So the sum is 0.358, and what comes out, these are the three sums, they sum up to 1, and what comes out is that Dick is the best. Through a sequence of pairwise comparisons. Okay, you may say this is too complicated. I would prefer to pick up just one that, according to my perception, is the best at the beginning, and I would save this complicated process. But indeed, you may see a nice feature of this decision process. The nice feature is that it's transparent. Once that you put numbers there, you have a decision that results from numbers, and you know, it's much more clear. And of course, it is clear